Chapter 12, Vectors and the Geometry of Space. Section 12.1, Three-Dimensional Coordinate Systems. The coordinate axes are three directed lines through the origin that are perpendicular to each other and labeled the x-axis, y-axis, and z-axis. The direction of the z-axis is determined by the right-hand rule, as illustrated in the figure. So we basically use this rule where we put our thumb perpendicular to our index finger, perpendicular to our other fingers, so that we can indicate that we're going in the positive z as we go up, and we're going in the positive y as we go this way, the positive x as we go that way. Then the three coordinate axes determine the three coordinate planes illustrated in this figure. So these three coordinate planes divide the space into 8 parts. So here's the closest part, one part, then there's another part behind, another part behind, another part behind, and then underneath there's another 4 parts underneath the xy plane. So these parts are called octants, kind of like your quadrant, but because there's 8 of them, we call them octants. And the first octant is this one in the foreground, the closest one to you. And it's determined by the positive axes. So you could think of the xy plane as being on the floor, and the yz plane and xz plane being on the walls. Remember that the planes are infinite in every direction, so even though we just draw them as squares, the xy plane keeps on going infinitely, and so do the xz and yz planes. We represent a point P in space by the order triple ABC, where A is the distance from the yz plane to P, B is the distance from the xz plane to P, and C is the distance from the xy plane to P. We call A, B, and C the coordinates of P. So A is the x-coordinate, B is the y-coordinate, and C is the z-coordinate. Then the points AB0 and 0BC and A0C are called the projections of P onto the xy plane, yz plane, and xz plane. So for example, if I'm thinking about the point 3, 6, 10, so then I would go 3, 6 in the xy plane and I'd float up 10 somewhere. Could be like, I don't know, somewhere floating. And then if I just wanted the projection, I would drop that 10 and it would drop it all the way down over here to the xy plane. It would just be 3, 6, 0. So that's what we call a projection. It's kind of like the shadow of the point. Lastly, the Cartesian product r cross r cross r is equal to the set of all ordered triples x, y, z of real numbers, and is denoted by R3. It is called a three-dimensional rectangular coordinate system. Cartesian product is just a fancy way of saying take some set and stick all of its possible values in the first coordinate of an ordered tuple, and set for the other set all of those possibilities in the second one. So there's just basically every single possible combination you can have of real numbers 3 ways. Similarly, R2 is r cross r, just your xy plane. So as an example of this, let's see what surfaces in R3 are represented by these equations. Well, if z is equal to 3, that's every single possible point where the z-coordinate is 3. So x and y can be anything. So I think I should just get a plane. Let's see if I can draw that. Draw my y-axis like that. I'll draw my x-axis like this, so I could put a little bit of it behind the plane. So I'll put the plane something like this. Yeah, roughly. And that way I can put my x-axis behind it, and I can put my z-axis behind it also. I should probably puncture through at some point though. How about I puncture through over here? So then this will be in front of it. So this is my z-axis, and then I punch through at 3. So that means that at 3, if you look at this part of the z-axis, that's above the plane, and this part is below it. You should think of the plane slicing through perpendicular to the z-axis, Remember, I drew it as a rectangle, but it goes infinitely in all of these directions. So we get a plane for z equals 3. How about y equals 5? Well, that'll be another plane. It's every single possible coordinate where y is 5, but xz could be anything. So let's see if I can draw this guy. Always so difficult trying to think about where to start when drawing 3D shapes, at least for me. So I'll puncture through at 5. I'll draw my y-axis like this. So this part is behind, and then it goes through. And I'll put my z-axis behind also. And then I need my x-axis. So then, there we go, roughly. Hopefully yours is a little more straight. Okay, so that's a plane again. And I'll put 0 over there, why not? Notice that in the xy plane, if I didn't have these three-dimensional coordinates, I would just have the line y equals 5, which is this guy. So if I were just to draw on the xy plane, you could think of it as, let's put another color, you could think of it like this line at 5. So that would be this line right over here. You can almost think of that as the projection of the plane onto the xy plane. So in R2, it's a line, but in R3, it's a plane. So you have to be careful about the context of your equation, because it can mean different things. This said in R3, so we drew a plane, but if you were just doing what you were used to, you wouldn't be wrong by saying it's a line. Okay, which points x, y, z satisfy these equations? X squared plus y squared equals 1 and z equals 3. So we know x squared plus y squared equals 1 is a circle in the xy plane, and z equals 3, so it looks like it should be a circle that's floating up at z equals 3. So let's see if I can draw that. Okay, here's y and x and my z. I want to put 3 over here, and I'm going to try to draw a rough circle, something like that. Notice it looks a little bit oval shaped because I'm not looking at this straight down. If I was looking down the z-axis straight down, then it would look exactly like a circle, but because of the perspective here, I had to draw it a little bit oval shaped. It's always a little bit awkward drawing in 3D. So this is a circle. The radius of our circle is 1, and the center of our circle is 0, 0, 3. Notice the center of the circle is on the z-axis. So how about if we just had x squared plus y squared equals 1? You might say, well, you already had that, but we didn't. Over here we had a restriction on z, where z had to be 3. Over here, for part B, there is no restriction on z, it could be anything. So that means that not only is it the circle at z equals 3, but it could also be the circle at z equals 4, it could also be the circle at z equals 2, it could be the circles anywhere along the z-axis. So it's an infinite number of circles that goes infinitely up and infinitely down. It could even be z equals 3.5, it could be anywhere. So what we get is this cylinder. I'm drawing the cylinder with a top, but the cylinder has no top. It continues infinitely. It has no bottom either. It's kind of like a plane. But just like I can't draw infinite planes, I draw them as rectangles. I'm just going to draw this infinite cylinder as a cylinder. and its axis is the z-axis. So I'm drawing that. Want that to be out in front. And let's do a little bit over here. Okay, put that 0 over there. And then we get a circular cylinder where, again, the radius is 1. But in this case, it doesn't really have so much a center as it has an axis. And the axis is the z-axis. I guess you could think of that as its center if you wanted to. Okay, how about the surface in R3 represented by the equation y equals x? So remember that in the xy plane, let's see if I can draw this. In the xy plane, y equals x is just a line. And it's a line that cuts through diagonally across the xy plane. So what I'm going to try doing is draw a diagonal line. So I'm going to do this dashed because I'm going to want this part behind the plane. Let's see. And then I want a diagonal line. So here's the xy plane. Here's positive y and positive x. So you could think of it just in a different perspective than what you're used to, but there should still be a line y equals x. And the only difference is that z has no restriction here. It could be anything. So the line could be floating up and down infinitely. So we get a plane. So it's really this plane over here. And here's the z-axis. And we have our plane y equals x. So that means that instead of writing x, y, z, I could write x, x, z, because y is equal to x. So it's all of these points x, x, z, such that x is in R and z is in R. Okay, how about the distance formula in 3 dimensions? Remember that in 2 dimensions, just the Pythagorean theorem, just this square root of the difference between these 2 points. While in 3 dimensions, it's the 3-dimensional Pythagorean theorem. You can prove it by drawing a box and then getting from one point to another in the box and then from the next to the next. And you can see that the way you're doing it is you're just getting the square root of each of those distances. Since you just have to travel one extra triangle up, you just get one extra difference to add. So let's get the distance between points P and Q given in example 4. So we have the distance between P and Q given by the square root of the difference between each of the points squared, each of the coordinates squared. So 1 minus 2, because I'm starting with Q going to P, but it doesn't really matter because I'm squaring anyway, so the order doesn't matter. But next to be minus 3 plus 1, because minus minus 1 is plus 1, and then 5 minus 7. So I square each of those, take the square root, that's the square root of 1 plus 4 plus 4, which is 3. Okay, how about the equation of a sphere with radius r and center HKL? Well, I'll draw my axes again. So here's z, y, and x. And I need to draw a sphere somehow. So you might want to close your eyes for this. Yeah, a little bit bigger would be nice actually. Okay, so here's an arbitrary sphere floating somewhere. Give it a little bit more perspective. So we'll put the center of the sphere over there. We'll say that's C with coordinates H, K, and L. And we will say that the Radius of the sphere is r. And then here's an arbitrary point in the sphere P with coordinates x, y, and z. So to get the equation of this thing, well, its defining characteristic is that the distance from P to C is equal to r. So we could write distance from P to C must be equal to the radius r. Well, it's the same thing as the distance from P to C squared being r squared. And the distance from P to C is given by the distance formula we just had. So that's x minus h squared plus y minus k squared plus z minus l squared equals r squared. And I don't need the square root because I squared it. Notice that if I was to take this circle and I was to move the center to the origin, then all of these guys, h, k, and l, would become 0. And I would just have a circle with the equation x squared plus y squared plus z squared equals r squared. So it's just like the equation for a circle, but we have a sphere because we just throw in an extra z thing. Let's show that this equation is the equation of a sphere and find its center radius. Similar to in two coordinates, you just complete the square. So we just have x squared plus 4x. So we'll add another 4 to that to complete the square. And we'll remember to add that on the other side of the equation also. And then we've got y squared minus 6y. So we'll have to add negative 3 squared, so we'll add 9. And then we've got z squared plus 2z, so we'll add half of 2 squared, which is 1. And we were equaling this negative 6. So we'll have to add everything that we added. So we added 4, we added 9, and we added 1. So we end up with x plus 2 squared plus y minus 3 squared plus z plus 1 squared equals 8. We just factor each of these terms and then we simplify the right side. So it looks like that is a circle with center minus 2, 3, minus 1, and radius square root of 8, which we could write as 2 rad 2. Okay, how about these inequalities? We've got x squared plus y squared plus z squared greater than or equal to 1 and less than or equal to 4. So we could rewrite these inequalities and we could take the square root. Square root of 1 is 1. Square root of x squared plus y squared plus z squared can stay that way. And then square root of 4 is 2. So that means that these are all the points whose distance from the origin is less than or equal to 2 and greater than or equal to 1. So less than or equal to 2 is a sphere of radius 2 and everything inside of the sphere because it's a less than or equal. Usually for spheres we only consider the surface part, not the inside, but because of inequality we also have the inside. But it's everything that's greater than or equal to 1, so it does include that sphere of radius 1. So it should look, let's see if I can draw this thing. Put the z-axis over there, put y over here, and x over here. And hopefully yours is less wiggly. Alright, let me try drawing my first sphere of radius 1. Alright, put 1 over there. And I'll draw my second one of radius 2. And now I'll cheat and make my axis a little longer. Okay, let's try to give this a little perspective. I'll draw underneath it a little bit. So over here is 2. Notice that what's happening here is that it's all of this stuff over here. And also a little bit, it's on the inside too, but over here on the inside, it's like there's a scoop out. You should think of this like kind of like a melon, that somebody took a scoop right out the center of it, because it's this kind of thick rind of the sphere, and the scoop doesn't go all the way through. It just scoops out another smaller sphere from the bigger sphere, and the region we're considering is just all of those points in between them.